So it's my great pleasure to introduce Viktor Vafeiadis, who I have known for almost 2 decades. And one of our very first papers was on concurrent program verification and building tooling for this. And I'm very excited to hear where it has got to now in actually scaling, because before, when we were looking at it 2 decades ago, it was like 4 or 5 lines of code. So I'm interested to see where we are.
Yes, well, thank you, Matt. So, okay, I guess it might be a bit longer than 5 lines of code. So, in a sense, the tool that I'll be talking about today does less than the tool that 2 decades ago. That there it was proving correctness, supposedly, for an arbitrary number of threads. Here it's for a bounded number of threads. It's supposed to be more automated, on the other hand. So, let's see. So what is a grand challenge of software engineering? Or wonder. We want to produce software, presumably. No? Or somebody else to produce software for us. Okay. That is, most importantly, efficient. Second, okay, correct. And third one, also useful. With minimal cost. So, no expertise required by developers, no time, no effort, use LLMs to generate the software for you, or the spec, everything, and you're done. Well, okay, this is the grand challenge. I'll not quite tackle this. I'll tackle a simplified version, where efficient means a concurrent program for me. Correct means I'll use a verifier to prove though. Useful, I don't know what that means. Maybe satisfy the specification if you like. Minimal cost to me, okay, let's use automated verification. So the cost is just compute time. And okay, to have minimal developer cost time, let's at least have a system that will never say, okay, I can't prove your program and stop. Or if it fails to verify your program, it will give you a concrete counterexample, a trace of the program execution that exhibits the error. So it is a real error. So that's what I'll be talking about. And the general technique that I'll be using is model checking. So what is model checking? You're given a program and a property, and you want to check that all executions of the program satisfy the property. So in my setting here, the program is a multi-threaded program, and the property is some safety property. So the program does not crash, or there are some assertions sprinkled inside the program, and for all executions of the programs, these assertions should be satisfied. So it's a fully automated approach. Usually you just run the tool and at some point it terminates. So one has to provide only the program and the property in principle. It supports weak memory consistency quite easily. You just generate all the executions according to your weak memory consistent memory model. And it has a nice effect that whenever there is a bug in your program, it produces an execution of the program leading to that bug. That's the nice part of the story. There are some problems. One, it assumes that programs are bounded, have some finite size, and probably some small size. It tends not to scale very well. And one still has to write the program and the property. So in the rest of the talk, I'll try to address these 2 issues here, the one of scalability and of writing the program and the property. Okay, so there are roughly 3 approaches for doing model checking. The stateful approach, which is you just, since your program has finite state, you just explore all the possible transitions of your program and record the set of states that you have visited. And if you visit the same state again, you've found that your program cannot terminate, fall in an infinite loop. If if you do not visit the same state, at some point you've covered the entire state space and you're happy. So it uses a lot of memory. You have to store all the states of the program, but okay, it works if your program is small. Now, there is the stateless approach, which tries to do the same thing, but without remembering the set of visited states. Why do you want to do that? Well, maybe these states are too many, so you just don't have the memory or the patience of recording them all. And if you do it this way, the one thing that you lose is you lose the ability to handle non-terminating programs, because you do not remember the set of states that you have visited, so it could end up in the same state again and again. So, and the third approach is to encode the entire state space of the program in the search inside a SAT or an SMT query, and then you ask the solver to explore the state space. So, in a sense, this third approach has at least the potential of exploring the state space in a more efficient manner, but it certainly suffers of the need to record not only the state space, but also the program and all the decisions made. So this also suffers from a lot of memory requirement. The other sort of benefit, sort of pros and cons of the various approaches, the first two approaches, stateful and stateless, you can estimate more or less how much time it will take, a very long amount of time. Whereas for the SMT-based techniques, you don't really know. It might find a heuristic and finish instantaneously, or it might take forever. And it's very difficult to tell. So what will I be doing? Well, at least my tool is one of the stateless kinds. So it has these properties, uses very little memory, works for weak memory consistency models, and okay, it's a correct technique and very parallelizable and so on. So let me now go to the actual content of my talk, which is how do we think about the scalability bottlenecks of model checking and how we can improve upon them. And then I'll talk about the specification problem. So, what is a problem? Is that given a program that is multi-threaded and otherwise sort of deterministic within each thread, still there are many, many interleavings of your program. It's an astronomical number of interleavings. So you cannot just explore all the interleavings in any reasonable amount of time. However, you do not need to explore all the interleavings, and there are various optimizations that you can do. So the simplest one is this partial order reduction, also dynamic partial order reduction, where you observe that if two threads access disjoint pieces of data, then it doesn't matter in which order you interleave them. And even at a more fine-grained level, if two instructions of different threads just commute, it doesn't matter in which order you execute them. So just choose one of the two orders. The second observation is that many times your system has some symmetry inside. So you have, let's say, two threads doing the exact same work. And then it doesn't matter which one executes first. So that's the notion of symmetry reduction. You can also find symmetries not at the thread level, but inside algorithms. Let's say multiple threads trying internally at some point trying to write the same value to location. It doesn't matter which one goes first. And you can exploit that to improve performance. And the final one, well, these two are sort of sound ways of reducing the search space. The final one is an unsound way of reducing it, but still very useful. And this comes from the observation that a bug typically can be found with many different executions. And, well, if you want to find the bugs, it suffices to look at a sufficient number of executions. Don't need to look at all the executions to find the bugs, or the common bugs at least. So if you can partition your executions into a class of simple ones and more complicated ones, if you can explore only the simple ones, at least you will have found all the bugs exhibited by the simple ones. There is some experimental evidence that with the simple ones, at least you can find almost all the bugs present. There is also, again, some evidence that with simple executions, it's more likely to understand the cause of the bug and therefore for a developer to fix it. Peter?
Curiosity, really evidence that you can find almost all the bugs versus merely a whole bunch of bugs?
So you can characterize classes of bugs, like violations of atomicity, which means that there is a thread that read a variable and then read it again, and in between the value changed, whereas the code assumed that the value didn't change. And such a bug can be found with exactly one interleaving, one context switch in between the 2 points. So there are classes like that that can be found with a small number of context switches. Yes?
You mean things like context bounding?
Yes, context bounding.
Is there a formal definition of a simple interleaving, and what does intuitively make an interleaving simple?
Yeah, so there are various ideas. So the simplest one is context bounding, which says that you have a scheduler that non-deterministically picks which thread to write, and you invoke. So you pick at the beginning one thread to run. You run it for some time, and then at some point you stop it, and you invoke the scheduler again. Pick another thread, run it, invoke the scheduler again at some point. Now, the number of times that you've invoked the scheduler, this is the number of context switches, and you can explore executions with up to some number of context switches, up to, let's say, 2 context switches. That would be executions of bound 2. And you can try to explore only those executions.
Okay, but there are many definitions for simple.
There are many different, yes. There are other definitions where sort of all the threads execute in a lockstep fashion, and the number of times that they're not in lockstep is your bound. There is another one that says that I'll have a round-robin scheduler among the threads, and each time I interrupt a thread and move to the next one, that's my bound increment. So let me just, without going into technical details, let me just give you an overview as to what is easy with model checking and what is difficult. So the first program is a program using arrays, nested things, and so on, but where each thread really accesses disjoint data. So if you run this program, okay, if you consider all the interleavings, there are too many, but if you use partial order reduction, you will get exactly one execution, because you'll notice that the threads are commute with each other. And so the verification time is really the time that you need to construct one execution, and that's sort of linear in the size of the program, the number of threads. Now, that's the best case. And sort of the worst case is if you have all the threads sort of accessing the same location. Then sort of here, so let's say you have a lock. You can understand it as having some lock variable that you do a compare and swap and change from 0 to 1 to acquire the lock. and back to 0 to release it. So there are a factorial number of ways in which thread could go first, and which second, and which third. So verifying this program, even if it doesn't do anything, is, let's say, difficult, it's slow, whereas verifying the top program is fast. Of course, okay, the second program doesn't have an assertion, but assume there's more stuff and some assertion. So, as an example, let me just explain sort of how one would implement reader-writer locks. So my tool does not support reader-writer locks as a built-in primitive. So suppose we want to add them. So how should we implement them? Well, the straightforward implementation is to count the number of threads that have acquired the lock in a read mode. What does that mean? Is that if you have multiple readers here, now you essentially, they all race on this counter, incrementing it and checking whether it's there is a writer and things like that. So in principle, unless you do other optimizations, you get a factorial number of executions. Which thread acquired the reader lock first and which second? So that's not how you would want to specify a reader lock if you want to use model checking. So is there a better way? Any ideas?
You don't need to interleave each of the reader sections because it's the same value. It can't be changed.
Yes, okay, that would be some way of some higher level understanding that all of this is supposed to be atomic, and you could sort of reorder them. Yes, they commute with each other. Yes, that can be done, but it's substantially more difficult. And perhaps the client uses the reader lock in an incorrect fashion, in which case the optimization wouldn't work. There's a simpler way, which is to just have a different implementation of reader-writer locks. One that you would not use in practice, but that provides the right semantics. And the idea is to have one lock per thread. The reader just acquires its own lock, which you might think is not very useful, but a writer acquires all the locks. This means that readers will not synchronize with each other at all, because they would be acquiring locks of different threads. Well, concurrent readers would not be synchronizing with each other, but a writer will be synchronizing with all the reads. So in particular, in my toy example here, you just get a single execution of the program, and therefore fast verification time. I will not talk more about of how to make model checking more scalable, but I gave this example precisely to stress the point that modeling of atomic primitives or of parts of your algorithm that you're trying to verify is important if you want to achieve scalability of verification. And the first model that comes up in mind might not be the best one. Yes?
So, what is the correctness property, or the relation between this implementation and the actual implementation that you need to know that you're checked enough? Because it is different, it is checking different traces for the research. I don't think we'll have, but somehow they're equivalent.
So here we're specifying, well, essentially we're specifying the reader lock. In terms of synchronization and correctness, it's that this implementation here synchronizes less than the previous one. So the client can observe more behaviors with this implementation of a reader lock than the incrementing one. In a sense, the previous implementation that keeps a counter is a wrong specification of the reader lock. It's because it's too tight. Azealia.
This implementation, the same thread can't acquire the reader lock twice.
Well, it cannot, at least as I've implemented it or shown naively here, it cannot acquire the reader lock in a nested fashion. But it can read a lock and acquire it again. If you wanted to do it in a nested fashion, you could use a counter instead of a lock.
This also doesn't support any kind of message passing of the unlock being on a different thread.
Yes. It doesn't.
So when I first read this, I was wondering, how does the writer find all of the threads whose locks it needs to take? And then I noticed that your slide says it acquires the locks of all the threads. But if half the threads were doing this on variable y, and half of them were doing it on variable z, and let's say they were writing rather than reading it, then you're going to have unnecessary contention there, aren't you? Between the threads writing y and the threads writing z.
So for each instance of the lock, you would have one lock per thread. So if you have a reader lock for variable x and a different reader lock for variable y, then you would have 2n locks. So one per thread and per variable.
Right, so, right. You could end up with a large number of locks then.
Yes, for specification purposes.
But as Victor said, I mean, this implementation of the reader-writer lock is just for verification. In practice, you wouldn't use that one.
Yes.
Just a lot of similar properties.
So let me go now to the second topic, which is how do you write the program and the property? Well, I guess you have to write the program, or somebody has to give you the program, but I'll make it a bit more specific in the case of concurrent data structures. So roughly, what you're given is an implementation of a concurrent data structure like a queue, but you cannot just give the queue to a model checker. You have to write a client, a test program that uses a queue, exercises its operations in a certain way, and asserts something about the return values, and then you can send this program to the model checker. So you have, and this is more or less the state of the art. Actually, it's a bit better than this, but this is what is done wherever a model checker is being used. It can be a bit tricky to write these programs if you want some sort of coverage of the behaviors of a client. Well, you might think of a few clients like this. You may need a few more. So what is a standard way of defining correctness of concurrent libraries? And that's the notion of linearizability. That's a notion that each operation, an NQ or a DQ, takes some time, and but they're supposed to behave atomically, as if they happen at some instant between their invocation and their return. So given an execution, sort of it's called a history in the linearizability literature, that returns certain values for the methods, you have to find some total order in which the methods execute, and that gives the same values as responses. And this total order should respect the real-time order in which these operations execute. So here, this example, NQ1 finished before DQ even started executing. So in the total order, they should be ordered in that way, not oppositely. But where two methods are overlapping, like the two NQs or the second NQ and the DQ, they could be ordered in either direction. And this corresponds roughly to having a global lock and saying that the specification of my method is like acquiring the global lock, doing the code, and releasing the global lock at the end. And essentially, we're talking about refinement of this. So how does linearizability help us? Well, if we had a tool to verify linearizability, we would go back to the clients that we had before, and we would delete all the assertions. We don't need to write them, in the sense that these assertions are checking for particular bad executions, particular non-linearizable executions of the program. And if we were to check linearizability for all of these clients, among the things that we would check would be these assertions. So how can we check the linearizability of a particular client of a data structure? You can do it in two phases. First, you analyze the client applied to the specification, so to the atomic implementation. And you record, and you sort of model check that program and record the set of valid outcomes. So the set of possible return results of the methods. You store all of that set somewhere in memory, and now you do the same thing with the implementation. So you plug in the implementation to the client, and you exhaustively enumerate all the executions of that. And for each execution, you check that the return values of the methods are among those that are allowed by the specification. So this was done also quite some time ago. And in fact, the second phase was done using a SAT solver, not by explicit enumeration. But the basic idea is this. So let's add weak memory consistency to the soup. And what do we get? Well, first, there is no such notion of a real-time order. That is, in the definition of linearizability. We said that in linearizability, there must exist this total order that preserves the real-time order of methods. There is no such real-time order. Okay, that's fairly easy. We choose some other order given by the memory model. In terms of the C++ memory model, we could choose happens before as a substitute there. But the second and most important thing is that the standard definition just talks about the outputs of methods, and it doesn't talk about any synchronization induced because of the library. So if I have an example here, I have two threads, one sort of, initializing x, then enqueuing a value, and if the second thread dequeues and gets this value, should it see here necessarily the value 1 of x, or can it also read 0? So this is something that the specification of the queue should describe. The standard specification would say that the enqueue and the corresponding dequeue synchronize, but that, anyway, needs to be mentioned by the spec. So how can we now specify a queue, a concurrent queue in the weak memory setting, saying that this synchronization should appear or not? Well, what's the simplest way? Let's use a global lock. Take some sequential implementation of a queue, whatever, and wrap the methods with a lock. So that is a specification, but it's not the most useful one, because it enforces all the operations to synchronize. And this is not usually the semantics you want. So what could we do instead? Well, if you're clever, you could try to use the C memory model with all its different atomics to try to write a very careful specification that gives you the exact synchronization you need. It can be done, at least for Qs. I have written such a specification, but it's more complicated than the program that we're trying to verify. So that's probably not the way to go. And there's this middle ground of using a specification device called a library scope lock that behaves like a lock. It gives mutual exclusion inside the library, but it does not induce any synchronization sort of outside to the clients. So it's not something that exists in practice, it's just a specification device. So it helps you to disentangle specifying the atomicity of the Q and specifying which operations synchronize. So to specify the synchronization, you can use the C11 atomics, but for atomicity, you just use these non-synchronizing locks. So my specification using these locks is almost the same as before, with the difference, or the subtle difference here, that I would say that this is a release store, and somewhere here there's an acquire load, so that the NQ, so that the DQ reading the value written by that NQ would synchronize. And so this specification would have precisely synchronization between matching NQs and DQs. If you want, you can have another specification that synchronizes more. Let's say you could synchronize all the NQs together. Use also another lock, a normal lock, to synchronize NQs. Yes?
Why isn't that already implied by the library lock? Why do you need to say that on top?
So the library lock, in essence,
Or is the idea that these are sort of exported to the rest of the program?
Yes,
okay.
Exactly. So yes, indeed, the release acquire ones are, but the library lock ones are not.
Maybe I have another question.
Yes.
Why do you need to annotate specifically one access as opposed to saying this specific function has a linearization point and you have acquire semantics from the linearization point or release semantics to the linearization point?
Well, so this is a specification. It's not the implementation. So, all of this is atomic in a sense. It is the linearization point. Oops, sorry. The linearization point is essentially all of this.
Yeah, but that's what I'm saying.
Yes.
Why do you need to annotate a specific access as opposed to the whole function? Because at the end, the function becomes a point.
Okay, so you have this back pointer, let's say, here, in the specific example, that all the NQs increment. So if you were to say that this is also some sort of release, then, okay, you're also reading it to increment it. So if it's also an acquire release, then at least all the NQs would be synchronizing. Well, okay. Okay, even if it's not. So here the back pointer is red. So if this were also an acquire, then an NQ would synchronize with all the DQs. So at least happen to see this update. Not just with the one reading. You can write such a specification, just be a stronger one. Yes?
When you build your model, then you say the size of these different, like back and so forth, you know, how many bits wide they are and so on, so you can put them, do they get transcoded into the model that's checked by the model checker?
Yeah, so all of these are word-sized accesses.
So 38 bits or something?
Yes.
Okay.
So how can we now check this relaxed linearizability, let me call it this, refinement, respect the a specification like this one here. So, pretty much the same way in 2 phases. We first generate all the executions of the specification, we record the set of outcomes. Now, outcomes are a bit more complex. They're not just the return values, but also the induced synchronization. And then we do the same thing for the implementation. We generate all the executions, and now for each execution, we check that the outcome is allowed. What does that mean? That there exists one of these recorded ones from the specification that has the same return values, and that the specification has less or equal synchronization than the implementation. The implementation can synchronize more than the spec, but not the other way around. The implementation can use a global lock if it wishes. That's all it's valid. So let me give you a simple example. It's the Hurley-Hewen queue. I will not show the code. I'll roughly show what it does. And a tiny client program. So if you analyze a specification here, you'll see that there are 3 possible outcomes. Either the DQ returns empty, or 1, the DQ is the first element, or the DQ the element of the second DQ. And these 2 induce a certain synchronization. We can analyze, we can now model check the client, the implementation, and we get various executions. One of them is this graph here, with events like reading, writing to various variables, some synchronizations induced. Now we can zoom out a bit and see, okay, what values they return. It corresponds to this sort of graph at the level of NQ and DQ events. And you see this is allowed by the final one down here with a few more edges. So this is checking linearizability for one particular client with weak memory as well. Well, the problem is that even without putting the assertion, finding the right client can be difficult. So this client here is the minimal client in terms of number of methods that exposes a bug in the Hurley-Hewen queue, or one implementation of the Hurley-Hewen queue that uses release and acquire accesses throughout. Well, this is a specific assertion, but it doesn't matter. So the point is, how can we prove correctness for all clients of a bounded size? The idea here is to use this most parallel client that just executes all the relevant methods in parallel. So here I have most parallel client with 2 NQs and 2 DQs, also writing distinct values. And the property is that if you take a particular client, a program, an execution of that particular client, it is an execution of this most parallel client with a few more edges, so a few more program order edges between the operations. So in a sense, this most parallel client is sufficient for verifying safety of a program, whether it reaches some error state. But on its own, it's not directly useful for linearizability because it doesn't impose any ordering among the methods. So these DQs could return 0, 1, 2, pretty much arbitrarily. But we will use it nevertheless. So what will we do? We will first analyze a specification, and besides finding the valid outcomes, for each outcome, we'll try to find the minimal additions that you can add, the minimal extra edges, or happens before orderings you can add between the method calls to make this outcome invalid. So here, specifically, if the DQ returns empty, and I make sure that the DQ is executed after NQ1, it can no longer return empty. And this, or if it's after 2. And similar for these other ones here. So what is it? Returns 1, Okay, it's after 1, but if I know NQ2 was executed before it, it cannot. Or if I know the DQ1 is executed before the NQ, obviously it cannot return this value. Now, I've colored some with yellow, meaning that these ones can actually be discarded easily, either because they create a cycle or because they violate some symmetry of the program. But anyway, you generate these outcomes. And then the second phase, you check the implementation. So you get an execution of implementation. You first check that there is a specification outcome with the same outcome. Yes, there is, good. And the new test that you have to do is for every recorded extension that invalidates the spec, you want to check that if you add this edge here to the graph, then this graph now is inconsistent according to the memory model. Specifically, this one here is whatever you read at some point 0 or no. Well, you read 0 here, although you have seen the writer. So this can be implemented and has been, and with sort of various optimizations for scalability purposes, it can scale up to 8 to 9 operations. And when I say so within minutes, it can prove sort of exhaustively linearizability of, let's say, eight clients with 8 operations. And and since this is an exponential thing, sort of if you do it with 7, it's 10 seconds. If you do it with 9, it's hours. If you do it with 10, it's days. And it finds very subtle bugs. So the bug that I mentioned for the Hurley Ewing queue with 7 threads, others with few less.
Did you just make up these bugs yourself, or where did you get these bugs from?
No, so you take the standard data structure, you put release acquire everywhere, and you check whether it gives you linearizability. So we make all the writes release, all the reads acquire, all the RMWs acquire release usually, and these are the bugs that you get. Yes.
The execution times you mentioned, they are for just one laptop execution?
Yes.
Because you mentioned in the beginning the parallelizability of your approach. Have you tried that?
Yes, okay. We've tried it on big machines, and indeed, the more cores you put, the faster it goes.
You can do it. So
you can do it, yes. That's all. Thank you. I've finished, and we could do more in the future.
We have a couple of minutes of questions for him.
Coming back to your counter size. If your counter sizes were bytes, maybe you would go to 11.
Question.
Mike?
So one of the things that's very appealing about linearizability is it looks very simple, and when you go to these more sort of like weak models, there isn't such a natural notion of like correctness. So I guess this is not totally related to what you're doing, but like, do you have any thoughts on like what is the natural notion of correctness for these libraries on these weak models? Is it something that looks like some specification construct, or is that something else?
So I think it is close to linearizability. So you want atomicity mostly, plus this what synchronization is induced. I think that's a good specification style. Now, whether you will do it in my way by writing code or write the induced synchronization somehow else, that's open to debate. So one interesting bit that I'd like to mention is that pretty much all the list algorithms do not satisfy linearizability. And they cannot be fixed unless you use SC accesses or SC fences. So this is a particular limitation. So if you want let's say an efficient set or an efficient map without SC, you cannot have linearizable-like specification. You have to have per key linearizability.
I have one quick question. So most of those data structures involve allocation when you actually implement them. So what's going on in terms of what you're actually model checking for allocation?
So each allocation gives you a fresh address, obviously, but so a specific fresh address. Now for deallocation, some of them have hazard pointers and so on, and we check conditions for the hazard pointers that are sufficient to show that the algorithm is correct. There's free memory that is used.
We're precisely on time, so let's thank you, Viktor.